Thank you. This was cool, and I'm really shocked that these guys actually survive what they do in the backcountry. Okay, so I talked about water and ice, and I tried to demonstrate that the formation of ice and the melting of ice is different from what we think. And I want to talk about evaporation, and the message is the same. It's not what we think. So what do you think about evaporation? You probably think that you've got a glass of water, and it's evaporating one molecule at a time. A molecule gets a kick of energy, of kinetic energy, and it comes up. At least that's what I learned. And the reality is a lot different. So let me start with this. This is taken at Starbucks. And Seattle, Starbucks was born in Seattle, so we drink a lot of coffee. And if you have a dark background, you notice this is a hot latte, I think, and taken by my son. And you notice something interesting. You can see the vapor. Now, if you can see the vapor, what does that mean? Well, you can see the vapor because the light is being scattered, and you don't see a hell of a lot unless the scattering entity is at least on the order of the wavelength of light. Wavelength of light is half a micrometer, where it turns out that these are little tiny droplets in here that are tens of microns. Now, even 1 micrometer little droplet contains, do you know how many water molecules? You can do the arithmetic. It's something like 1 billion on that order. So there's something wrong or appears to be wrong with the idea that the evaporative entity is 1 molecule, unless they come together above here. And we know they don't because we've checked we've checked these when water is evaporating, and we can check right just above the surface as this is emerging. It's no different from what you see here. So that idea seems to be incompatible with basic physics. Well, another interesting feature is that it's not continuous. Look, it seems to be discrete. Now that's a surprise because most of us, we presume that the evaporative process is a continuous one. Not only is it discrete, but also it appears to come from one region of the water, not necessarily from the entire surface simultaneously. Well, I have a lot of undergraduate students working in the lab, and many of them don't do what I tell them to do. They have minds of their own. And there was one guy, there's a Chinese student, we have a lot of them in Seattle, and he was curious, and so he took a laser beam, and what he did is to condense the beam into a plane, and he wanted to get a cross-section of one of these would look like. So what do you think they look like? You might think cross-section would look like kind of cotton or something like that, but it doesn't. It looks like this. These are 4 different experiments, and you can see, looking at, let's say, this one, that the bright area is scattering light. It means that's where the water is. In between that, the dark area is doing nothing, so it seems to be essentially empty. And I got to tell you that when I saw this for the first time, I almost fell out of my seat because I couldn't believe that the evaporative entity had structure just like this. It seemed inconceivable, but after enough repeats of the experiment, it was pretty clear that this was correct. So the first thing, well, sorry, it wasn't the first thing, but we thought, this is not created from nothing, this kind of pretzel-like structure. There must be something in the water that may be giving rise to this kind of pretzel-like structure. So we raised the question, is there a corresponding structure in the water itself? I'm not sure if you can see it, but I can see it on my screen. If you look into the warm water that you see here. And this picture was taken by my son, who's the artist of my book, and I was really pleasantly surprised to see this. This one was at home, I think, not in Starbucks, but I can see it here. I hope you can. There's a mosaic structure. If you can't see it, then take a look at this one. This is an experiment you could do yourself. So this is a pan of warm water, and it's illuminated not from above, but at a glancing angle from the side. You might call it dark field illumination. And you can see the same sort of structure, low angle illumination. And so it looks like the warm water that's evaporating does contain some kind of structure, as the previous slide showed as well. And we can also see it by using an infrared camera to look down at the warm water. And you can see same sort of structure. So there's no doubt that the structure is there. Well, the usual interpretation when you use an infrared camera is that this region looks warmer than this region. In fact, conveniently, they actually provide a scale for you so you can correlate the darkness with the equivalent temperature. But it's not necessary that that's the only explanation. Another possible explanation is that these lines actually denote the presence of easy water. Now, why do I think so? Well, it's because of older experiments that we did. Here's a piece of naphthalene next to water. And remember, an EZ forms next to the water. And so the infrared camera is picking up the amount of infrared energy that's being radiated from that. The EZ is dark. It means it doesn't radiate a whole lot. And the water beyond the EZ radiates, as you can see, is brighter. It radiates much more. So dark here, the EZ is dark. And if we go back to the infrared image of this, you have to ask the question, is it possible that the dark region here is actually EZ material? And we think it is because we've looked at the origin of these structures that form. And you can see little dots here, just as they form. And these dots, we don't know whether they're little droplets or little bubbles, but essentially it doesn't matter for us because what we found in our experiments is that if you have a droplet, this is the structure. If you have a bubble, this is the structure. And in both cases, these are lined by layers of EZ material, just like onion skin, and that's what holds it together for both of these. But inside, you have a lot of protons, and the protons are repelling each other. They're pushing out against this skin, and that's what keeps it into a sphere. The difference is that in this case it's liquid, in this case it's a vapor. So we've learned in our experiments about these water droplets, and since we don't really know if they're droplets or bubbles, we call them vesicles. And we do know that the vesicle structure looks like this, and we do know that as they form, before they enclose themselves, these positive charges tend to repel each other. They leak out, and so the amount of negative charge here is always more than the amount of positive charge. So these little vesicles, whether they're bubbles or droplets, have net negative charge. That's important. So if you think about the possible explanation for these dark lines, remember I suggested maybe they contain EZ material. Well, a possible way that they can contain EZ material is shown here, that you have a lot of these vesicles that are stuck together, and so for example, this entire cluster here would represent what we see here, consisting of a whole bunch of these stuck together. How are they stuck together? Well, we presume that they're actually glued by protons. And so these are negatively charged, and this is negatively charged. If you have protons between them, the protons will act as glue, holding them together. Now, this is not a wild speculation. It actually comes from Feynman many years ago. who talked about negative or like charges that come together, and he called it like, likes, like. Well, these negative charges like each other, so they come together. And he said the reason they come together doesn't violate any basic principles of physics. It's because opposite charges gather in between. And so you might have positive charge, which pulls this one and pulls this one. He said like, likes, like, because of an intermediate of unlikes. And I think that's what happens, and that's how you can imagine that these are actually glued together, negative charge here, protons in between, holding it all together. There are many examples of this. I don't have a time to present it. So this is an oblique view that shows the same mosaic structure on top. But what this slide shows is that it's not just the surface layer, it actually extends downward. You can see the dark lines coming and extending downward. And what that means is that these mosaic cells are actually mosaic tubes. They extend down into the water. And so when we talk about evaporation, we have a situation that looks like this. This is a kind of conclusion slide that we have these basically tubes that run down. They're not just on the surface, they run into the water. And when sufficient charge gathers, they actually rise up like this, and then they become vapor. And if you were to take a cross-section of this, it might look something like this. So basically, the vapor patterns that you see, especially in cross-section, come from liquid patterns that are down here. They simply rise up to give you this incredibly beautifully shaped vapor that we see. And you get clusters, so you get one of these groups of tubes that rise. Well, this will be the first one, then the next one, and the next one, and they're actually discrete events. But by the time you get up here, the droplets that make up these clusters eventually dissipate because you don't see any vapor up here. So they're basically dissipated into the air. And so when you think about humid air, you can think about these negatively charged little droplets surrounded by positive charges, which are known to occupy the atmosphere. However, if there's enough positive charge to glue these together and form clouds like this, then the humidity disappears and it becomes clear instead of humid. And then you can see a difference in your environment. So if you have humid air, you can imagine looking through this humid air to some building that sits at some distance. And the building is not clear, it's fuzzy. And the reason it's fuzzy is that the light that gets scattered from the building, before it gets to your eye, it's scattered by numerous of these rather large little droplets that sit in the air as humidity. On the other hand, if the air is clear, if these little droplets have actually condensed into clouds, then you can see these buildings much more clearly. So those of you who live on the East Coast, you know, Washington, D.C. in summertime, buildings look like this. But in the wintertime, they may look like this. Okay, so that's evaporation and the mechanism. I've presented evidence to you that the mechanism is grossly different from what we think. Okay, now what about condensation? So you've got these droplets in the air. How do they condense into clouds? Why do we get a cloud to begin with? So what we have in the atmosphere, among other things, are two principal constituents. One is these water vesicles that have a negative charge. And we have positive charges known, the atmosphere is known among atmospheric scientists to be net positive charge. And somehow the positive charges are linked, nobody knows exactly how, to molecules in the air. So we have negative charge and we have positive charge. And so we come back to the Feynman's like mechanism. We have these vesicles of water that are suspended in the air, and we have positive charge. If you add these together in the right quantity, you get a cloud, because the positive charge brings these negatively charged vesicles together. So a cloud may look something like this. Principally, these negatively charged vesicles, and with enough positive charge, these vesicles are actually linked together, and they form these clusters that we call clouds. So, question arises, what keeps clouds suspended in the sky? And I don't know, a lot of people have never thought about this question. Remember, it's water, and water is pretty heavy. Well, we know that clouds have charge. This is one example, probably not unknown to the electric universe people. We also know that the Earth has an electric field, beyond the magnetic field. And the electric field runs perpendicular to the surface of the Earth, and it exists because there are positive charges up here in the ionosphere and beneath, and because the Earth has a net negative charge. And by the way, the net negative charge may come from the EZ water that fills the surface of the Earth and all greenery. So this is the electric field at the surface of the Earth is roughly 100 volts per meter, which means that my nose is 200 volts relative to my toes. Okay, so good to remember. It's easy. Okay, so we have, what about floating clouds? So the Earth is negative, and the cloud is negative, and so it doesn't take a rocket scientist to figure out that there's a repulsive force between them. But your reaction might be, or might not be, is that repulsive force really strong enough to keep the clouds suspended simply by repulsion? I want to give you two examples that demonstrate it. The first is this. You take an old-fashioned 120-watt bulb, and the current is flowing through the tungsten filament, and suppose you could collect 1 second worth of charge flowing through here, just 1 second, and suppose, thought experiment, you could compress that to a point, and you put that point down here of negative charge, and you do the same thing up here, and they're separated by 1 meter. So the question I ask you is, you know that these are going to repel each other. This one can't go down, but this one can go up. So the question is, how much weight do you need to put on this one in order to prevent it from going up? Okay, so I've asked this question. I get all kinds of answers from a gram to a ton or whatever, and the right answer is about 50,000 garbage trucks. Now, knowing that there are Boeing engineers here, the original thought was actually it's something like 5,000 Boeing 747s, but my son, the artist, couldn't draw a Boeing 747 stacked up. So we wound up with garbage trucks, and this is roughly the amount of weight. Now, we're talking a huge force. Another example is this. So you have a couple, and the guy is lying here, and the woman is suspended somehow. It doesn't really matter how she's suspended. You might think of a net or something that's keeping her away. Of course, they would like to join each other, but she's suspended here. And suppose, this comes also from Feynman, by the way, from his lectures, except he has them vertical, standing instead of in this position. But suppose you're able to remove 1% of the electrons from this guy and 1% of the electrons from this woman. So she's positive, he's positive. They repel each other. He can't go down, but she can go up. He doesn't want her to go up. He'd rather have her go down. Well, so the question is, how much weight would you have to put on her back in order to prevent her from rising up? Anybody have a guess? How many garbage trucks? Okay. So actually, the number of garbage trucks is so large. The correct answer, remember, according to Feynman, is the weight of the Earth. This is astonishing. So main point. The force that is generated by charges is much larger even than people in the electric universe, or most of you are I think, thinking. Huge forces. And so we come back to what keeps the clouds suspended. And I think what keeps them suspended is the fact that the clouds have a net negative charge and the Earth has a net negative charge. So one suggestion is a repulsive force between these and these. That's why the clouds are sitting up there. And if the cloud has more negative charge, then it's going to be higher. And if it has less negative charge, then it's going to be lower. It's a simple paradigm, and that explains what atmospheric scientists have a really hard time explaining, and that is clouds in different layers. So simple explanation is that this cloud has a lot of negative charge, so it's high. This one has a moderate amount, and this one has low negative charge. And so that's how they're suspended. Side issue is this. Think about it. The Earth is negative. The atmosphere is positive. We all know that positive attracts negative, and so you'd expect that simply by virtue of the fact that this is positive and this is negative, they're going to stick together. Now imagine if they didn't stick together. Just think about this scenario for a moment. The Earth is spinning, right? And typical velocity on the surface is, we're talking about something like 2 times the speed of a jet plane. So it means if you went outside and the atmosphere was not stuck to the Earth, there'd be a hurricane outside every time you walked out. So I mean, the atmosphere must somehow stick to the Earth. And this is perhaps a simple explanation that plus and minus cling, and so the atmosphere clings to the Earth. And in fact, if you think about it, a question that might be raised is, does clinging force explain what we know as atmospheric pressure? We think of the pressure arising from molecules pressing on each other, but you know the atmosphere is not a pile of bricks. The molecules are a gas, which means they hardly touch each other, and you can go through various arguments to come up with an idea of how the atmosphere could actually press on the Earth, but a simple argument might be that the pressure comes from the plus sticking to the minus. And that prevents the blow-away scenario, because there are big winds up here, and if you just have stray molecules around and the wind comes, you might expect that we'd have no oxygen left to breathe. Okay, so I talked about the condensation. Now what about precipitation?